What is time? A clock is something that ticks, but what is the tick and how do we measure it? The Earth goes round the Sun once a year. That's a clock. The solar system moves around some larger object. Here is another galaxy. Galaxies moving around larger and larger objects. At the largest possible scales, we envisage long clock ticks. The cosmic microwave background radiation marks the light boundary of our universe, the limit of what we can observe. Light, as we know, is a form of energy. Energy is related to time by the uncertainty principle, which is at the foundation of quantum mechanics. Energy is characterized by its wavelength or frequency, as in the musical tone of an organ pipe. The relation between the wavelength and the frequency is the speed of light in the case of light. The first source of light that we observe is the cosmic microwave background radiation from the so-called early universe. And from astrophysical observations, we know that these so-called CMB photons change their frequency as they move through what we think of as the history of our universe. Their lowest temperature is about 3 Kelvin, which is very, very cold, and it happens to correspond to a theoretical mass for a right-handed neutrino. In the theory that relates the CMB to the neutrinos, there is a correspondence between bosons and fermions, which we expect on mathematical grounds, and it's very simple. It relates neutrinos to photons. It should not be surprising that the CMB has something to do with the generation of mass, because we know that inertia has to be cosmological by some old principles, such as Mach's principle. But by the uncertainty principle, a very precise energy corresponds to all of time. And we must reimagine time, starting from the discretization that goes along with quantum mechanics. Quantum mechanics rules the world.